Woohoo! All right, here we go. This video is going to be on what are called significant figures, significant digits. Either one means the same thing. In science, you want to be accurate and precise. You want to be both have accuracy and precision. Let's go over what those mean. Accuracy. If you're accurate, right? Accuracy, that means you're close to the standard. All right, there's an established value for something, and you're accurate if you get close to that. So, for example, we all know that the boiling point of water at sea level on the planet Earth is 100 degrees Celsius. We know that, right? You know that. So 100 degrees Celsius. Let's say that you're doing measuring of water at sea level, and you get a measurement of 99.9. Call that pretty accurate measurement because you're close to the accepted value. Great. What if you, however, so this means there's a standard value, and you are close to it. Or maybe you're spot on. If you measure 100 degrees as a boiling temperature water, that is accurate. All right, now what about precision? These words sometimes get used interchangeably, and they don't mean the same thing. If you have precision, that means you are consistent. You can do the same thing over and over and over again. It doesn't mean it's right, but you can do the same thing over and over and over again. So being precise would be as follows. I have a thermometer. I'm at sea level and I'm measuring the boiling temperature of water. The thermometer measures 80 degrees. All right, we go, that's not very accurate. But I take a second beaker, boil that, measure it with the same thermometer, and I get 80 degrees. And I take a third beaker of water, measure the boiling temperature, boil it, measure the boiling temperature of that thermometer, I get 80 degrees. That's 3 times in a row, 3 different situations where I get 80 degrees. Now we know 80 degrees is not the boiling temperature of water, so we would not say that's accurate. So you could be one or the other, or you can be both or neither. That would be precise, however, because you did the same measurement over and over again. You repeated the same thing over and over again. You were consistent in the wrong value, but you were consistent in it, and that would be a precise. So this has to do with being able to repeat something over and over and over again. Be consistent. Well, in science, we want to be both accurate and precise. We want to get close to the accepted value, and we want to be able to do it again and again and again. So that's what we're looking for when we talk about things getting be accurate and precise. We want to have that thermometer measure 100 degrees. If we're at sea level, it changes as you go up in elevation. The boiling temperature of water becomes less. But we would want to repeat that over and over again with our thermometer. All right, so that's the difference between accuracy and precision. Accuracy close to the standard, precision means you do the same thing over and over again, and hopefully you're both in your measurements. Measurements can come in all shapes and sizes. What are you talking about? I'm talking about, let's say that I measure something and it comes out to be 200. 200 what? I don't know, 200 whatever you feel like you're in the mood for. Tell you in the mood for kilograms, you're in the mood for meters, you're in the mood for liters. Hey, free country, you pick, right? But it's 200. I measure it as being 200. You ready? That's 200. That's 200. That's 200. That's 200. A little weird looking, but it's 200. Those are all 200. Some of those are better than the other one. What are you talking about? All numbers are created equal. Not all, all numbers might not are created equal, not all measurements. So this measurement up here, somebody said 200. Let's say it's meters. So 200 meters. Now, did they round that? Maybe it was 190 meters. They decided to round it to 200. Or maybe it was 203 meters. They said, close enough for government work, we'll call it 200. So we don't know how much this was rounded. It could have been 150 meters, and they decided to take the 5, round the 1 up, and make it 200. So there's a huge range of what this measurement actually could have really been. This one, this is 200. 200.0 tells me that it was exactly 200. Now, there could be some uncertainty in this last measurement. Maybe it was 200.01, and they decided to take the 1 off and just leave it as 200.0. Now, so there is a little bit, there's always inaccuracy in this last number in any of our numbers. We're not sure how much rounding there was. What was the person thinking when they were doing that measurement and recording that piece of data? So this one here, I know this is better than this one. Like we said, this one could be 150. This is, it's 200, but with a little bit of inaccuracy beyond that decimal point, beyond 200. So that's actually much, much better of a measurement than this one. This one, even better yet. I'm getting out here, I'm getting accuracy beyond the 10th point, beyond the 10th to the 100th point. So that's even more accurate. This is 200. 2 times 10 to the second is 200, but not as accurate as these two. And here's 200 as well. And these two zeros out here are kind of, you don't need them. You don't write 200 with zeros on it. You can, there's nothing wrong with that, but nobody does it. So, but this is still 200. This is actually the same number as this one. They are. This one and this one, same thing. I mean, we found out that this one's not very accurate. Oh, there was that word accurate. So in order to show how good a measurement is, how accurate a measurement is, we need to have what are called significant figures. The more significant figures or significant digits, mean the same thing, we have, the better the measurement. So we want to use a measurement instrument and we use it as accurate as we possibly can. We want to make sure that we get out as far beyond decimal points as we can, allowed by the instrument that we're using to do the measuring. So there are some rules to how good, accurate a measurement is, and here they are. I'll write these down for you right here. Any non-zero is significant. That's rule 1. Well, I won't call them rules because some of you are angsty, rebellious teenagers, so we'll call them guidelines. So that way you don't go, oh, okay, I'm not going to follow any rules. Okay, well, these are guidelines. Oh, okay, maybe I'll follow those guidelines. Okay. Pirates of the Caribbean? Yes. Some of you know what I'm talking about. So there's guideline number 1. Any non-zero is a significant, accurate number. Okay. The 2, the 2, the 2, the 2, and the 2. So are all good values, what we call significant digits. The next 2 rules have to do with zeros. Zeros are the things that are going to mess you up, the things you got to think about. Zeros, okay? Rule number 2. Any zero after the decimal point, comma, after decimal point, and last is significant. So any zero that's after the decimal point and last is a significant zero. Okay, the decimal point is understood to be here, and this is first number, and so that 200 doesn't have a zero after the decimal point, so these are not going to be significant zeros. So these don't pass rule 2, guideline 2, sorry. This one, however, 0.0, this is after the decimal point and it's the last number, last digit in that number. So that is, by this second guideline, a significant measurement, a significant digit. So I'm going to put a check over that. I put checks over the significant ones. Here, this second zero, last and after the decimal point, is considered to be a significant digit. Okay, this is 200. Actually, the scientific notation, we'll come back to that in just a minute. Scientific notation is going to help you get out of some quandaries, some problems, some issues that you might have doing math with this stuff. So we'll come back to that. This one here, no zeros after the decimal point, so no significant zeros according to guideline number 2. One more, guideline number 3. Any zero between 2 significant digits, any zero between 2 significant digits is significant. So, I mean, if you can read that, it says any zero between 2 sig digs is sig. So any zero that's between 2 significant digits, those are significant zeros as well. Okay, so let's check these 2 zeros out. These don't pass guideline 3 because there's nothing over here on the right of them that's significant to bracket them in. In other words, this is sometimes call it the bracket rule. If you have something on the left and something on the right that are significant, and anything in between those, they're significant. Right here, case 2. Significant because you're a 2. Significant because you passed guideline number 2 after the decimal point and last. You 2 zeros are in between those 2 significant digits. They are bracketed by 2 significant digits. Therefore, they are significant. Good and good. This one here, same thing. You've got a 0 and a 2, both significant. We have 3 zeros bracketed in between. They're all significant. That means this first 200, this is 200, 200, 200, but let's look at this. This is accurate with 1 significant digit. This has 1, 2, 3, 4 significant digits. This 1, 2, 3, 4, 5 significant digits. This is the best. The more significant digits, the more accurate, the better your answer is. So far, you're the winner, the winner. All right, actually, let's go down to the last one here. There are no significant zeros here, so I can't bracket any zeros in between them, so you also only have 1. You're the same number as this one. It's written a little different, but you're the same number. So you have 1. This one only has 1. Now here's why. The rule for scientific notation, and this is scientific notation. I'm not going to do a video on scientific notation. I know I had it in the list of topics, but I figure if you need review on scientific notation, look up a video on YouTube. You can just find them to do scientific notation. But I'm going to make the assumption that you do. If you don't, just look up a video. It won't take you very long. Scientific notation, any number that you put in front of the times 10, those are significant numbers. You don't even have to look at any of these rules here, guidelines. No guideline checkage here. You just have to know whatever you put in front of times 10, those are the significant numbers. So in this case, there's 1 because of this 2 here. So this would have 1. Now, if I wrote it like this, 2.0 times 10 to the second, that is also 200, 2.0 times 10 to the second. This would have 2 significant figures because I wrote 2 numbers out in front of the times 10. Oh, this is significant because after the decimal point. No, these rules don't apply to scientific notation. If you see something in scientific notation and you want to figure out how many significant figures it has, you don't have to think about the rules. You just have to count how many numbers in front of the times 10. This one is 2. All right? Now, we're going to come back to that. That's a great thing. Scientific notation helps us get out of a lot of issues when doing math, problem solving with significant figures. Okay, so that's what we have to do next. The next thing we're going to do is do some math. Let's do some math. Let's crank out some math with measurements and see what we get. And how should we report? We have to report an answer, write down an answer with the correct amount of significant digits. Okay, we have to convey to the reader how accurate my answer is by using the correct amount. Now, what are you talking about? What do you mean? Okay, let me give you an example. Let's say that we're doing a density calculation. Okay, density is one of the things that we need to know for this week. All right, density is mass divided by volume. Mass over volume. Okay, let's say we do a mass measurement. And the mass of something comes out to be 27.10 grams. The volume of it comes out to be 0.031 cubic centimeters. I'm just making numbers up here. Let's do the math. Let's see what the old TI-84 says. Let's see what the answer is. All right, let's see. Answer 27.10 divided by 0.031. Boom. TI-80 blah, blah, blah. Spits out this big answer. And I'll write it down for you. Here's what it is. It says, and try this at home. Don't trust me. Remember, I usually wear a tie. Don't trust those people. So this comes out to be 874.193548.4. Calculated its job. You gave it some numbers. It doesn't know anything about significant figures. The calculator doesn't know anything. So what it did, it spit out this number. How should I report the answer? Oh, like that, like the calculator. That's really accurate. Wrong. You cannot. You ever hear the saying that a chain is only as strong as its weakest link? The same thing is true here. The chain, the problem, is only as good, as accurate as its weakest link, the least significant number you used to get the answer. You can't have something this accurate when you only use numbers which only have that amount of accuracy. That's getting something for nothing. There's no free lunch. But you can't do that. So let's count out significant figures. This is where the rules guidelines come into play. This has 1, 2, 3, because those aren't zeros, they're all significant. This 0, guideline 2, is after the decimal point and last, so it is significant. So that's 4 significant figures in that top number. The bottom number has, okay, careful. I know I heard some of you said 3. No, 2. 2, why? Because the 3 and the 1 are not zeros, so they're significant. Yeah, but this number is after the decimal point. This number is after the decimal point. You said, no. I said yes, if it's after the decimal point and if it's last. This is after the decimal point, but not last, not the last number. The 1's the last number. So this is not going to pass rule 2. And there's nothing over here on the left of that 0 for guideline 3 to make it significant either. So this is a non-significant 0. Therefore, the bottom number only has 2 significant figures. Now, the answer has to be reported, reflecting the least accurate number we used to get it. So we got this number using these two. You have the least amount of significant figures. My answer has to have only 2 significant figures in the answer. That's all I can have. So you can start counting from the left. Count. 8. There's 1. 7. There's 2. Boom. Done. That's it. Oh, so the answer is 87. No. If I owed you $874 and I decided only to pay you $87 and that's it, you're not going to be happy. No, they're not even close. What we have to do is do 1, 2, stop, and then we see if this number behind rounds the 7 up. Does a 4 round a 7 up? The answer is no. Okay, you know that. 0 through 4 are not going to round a number up. 5 through 9 will. The 4 does not round that up to an 8. It was 8, 7, but I do have to fill in this spot because the decimal point's here. I need to fill that spot in with a 0. That's called a placeholder 0. It's not a significant 0, but it's important, not significant. I know it sounds like they're the same, but they're not. That's a placeholder 0. So that is 870. That should be how that answer should be reported with the correct amount of significant digits. All right, sig digs. Let's do another problem. So math, when it comes to dividing, which we just did, we just divided. And when we multiply, so divide and multiply, those are our first 2 examples. If we did a division, let's do a multiplication. Let's take 39.12 and multiply it by 0.00210. Okay, let's multiply those up. I'm just making these numbers up, so I don't know what these are. 39.12 times 0.00210 equals, calculator, drum roll, 0.082152. Calculator did its job. Thank you, calculator, but the calculator doesn't know about accuracy and measurement. You do. So we have to make sure we write this correctly. Okay, how do we do that? 1, 2, 3, 4 significant figures. There are no zeros here. How many here? Okay, careful now. We got some zeros to contend with. Look at our guidelines. If you're at the last number and after the decimal point as a 0, you are significant. Oh, so that 0 is good. Well, that 1 and 2, those are good. They're non-zeros. These zeros do not pass rule 2 because they're not last. They are after the decimal point, but not last. And they don't pass rule 3 because they're not bracketed in by anything on the left. If there was a 1 here, those would now become significant because the 2 and the 1 would bracket those in. But there was no 1, nothing on the left, so they are insignificant. 3 significant figures. Okay, the answer has to reflect the least significant figure number that I used. 4 and 3, 3. So my answer can only have 3 significant figures. Okay, here we go. Careful. Significant figures in the answer. 0.0. This doesn't count. That's not a significant 0. Remember? After the decimal point and last. It has to be after. So it's not. This does not pass a rule. So this is called a placeholder 0, but it's not a significant 0. And we have to have 3 significant figures in the answer. Okay, so keep going. So you're actually not going to count toward my significant 3. 8, 2, 1. Those do. 8, 2, now I gotta be careful here, there's 1. I stop there, I do not go beyond because I've got my 3 significant figures. But I do have to check and see if the 5 rounds the 1 up. Does it? Yes, it does. The 5 does round that 1 up to a 2. So this would be reported correctly and get maximum pointage on your academic adventures / test, which is a dirty 4-letter word and I don't like. 0.0822, 3 significant figures in the answer because of our least significant number we use to get it. Okay, that's multiplying and dividing. All right, we will take a quick break and come back for the last video on significant figures and of this week's topics. Okay, be back.